Good morning, physics student. This is Monday class, and we are continuing our study of waves. I hope you all are doing well. So today we will discuss some problems, and then we'll talk a little bit about transients and standing waves, and I'll come to at the end of this class. I'll come to discuss your microwave lab. Okay. Okay. So let's start with our startup. Okay. So in your notes, solve the following problem. Then you have a problem, very easy problem. You're gonna use your wave equation or wave formula to solve this one. Okay. So you can pause the video and start solving your startup. So first thing to note here is that this is a microwave. A microwave here is an electromagnetic wave, and it's also you're giving that it's in space. But this means that the speed of this microwave is equal to the speed of light, and you're giving also the frequency, so you can use the wave equation in order to calculate the wavelengths. Okay, so here's your answer. Again, remember that microwaves are electromagnetic waves, and then the speed of this microwave is equal to the speed of light, 3 multiplied by 10 to the 8th power meter per second, and then you can use the wave equation to get the wavelengths. And this is your answer, so it's 0.125 meters. This is the wavelengths of this microwave. Okay. Okay, let's take this one, and again, you can pause the video, but I'll read it for you first. So calculate the wavelengths of a microwave. Again, another microwave, and this time it's in air, okay? Given that the speed of the microwave in air is this number, which is slightly less, okay, slightly less than the speed, actually, yeah, it's less than the speed of light that you or a speed of any microwave um, propagating through a vacuum. Okay, so you're giving this value for this speed of the microwave in air, and then you're giving also in the problem the frequency in hertz. Okay, um, so again you can use your the wave equation in order to solve that to get the wavelengths. Okay, so it's easy. And you noted that in this case, the value here of the wavelengths is less than the previous one. So what happened here is that the speed of the microwave decreased as the wavelengths of this uh, microwave decrease as it passes through or as it propagates through a different medium. So it's not vacuum, it's air, and then there is this decrease in the wavelengths and decrease in the speed as well. So in this example, as the speed of the microwave decreases due to medium change, so from vacuum to air, the wavelengths decrease than the wavelengths in the previous example. So remember, the wavelengths of the previous example was larger than this number, okay? But the frequency remained the same, okay? So again, I think I told you this note before, but I'm gonna tell you again, okay? For waves in general, and especially for electromagnetic waves, when a wave travels from one medium to another, the wavelength changes with speed, while the frequency usually remain constant. Okay, so you have this exercise about sound waves and wave properties, especially for sound waves. So you have these four questions, and these four questions are represented in the diagram or the graph that you have here. So compare the images of the two sound waves that you have here, wave A and wave B. Uh, to answer the following quick question in your notes or in your physics notebook. Number one, which wave has a higher frequency? And then number two, which wave has longer period? Number three, which wave has greater amplitude? Number four, which wave has a higher pitch? Okay, so again, you can pause for a minute the video and choose the right answer. Okay, just look at the figure or the two waves, wave B and wave A and B, and easily from your knowledge you could pick the right answer for each of these questions. So if you look at the figure here for number one, you'll notice something that, okay, you have here the meter, the length, the amplitude on the y-axis, and then you have the time on the x-axis. So as you see this this wave, if you look at the figure, you'll notice that there are more cycles per unit time than this one. So here the frequency here is greater than the frequency here. So more cycles per time. So which one have a higher frequency? It's A. It's wave A. For number two, which wave has longer period? Remember, period and frequency are in the inverse of each other. So if you have a higher frequency, then you have less period, and vice versa. So the automatic answer would be B. Okay. So if you have a higher frequency in wave A, this means the period is short, and then for wave B you have a higher period, or longer period. Okay, let's move on to question 3. Okay, number 3, which wave has greater amplitude? Again, from the figure, you could note that both of them has the same amplitude. Okay, so both of them have the same amplitude, or their amplitudes are equal. Which wave has a higher pitch? So remember from last class, the pitch is associated with frequency. Yes. So the one that has higher frequency has higher pitch, so it's wave A. Okay. Again, remember that pitch is associated with frequency. Okay, so let's take this this problem, and again, I'll give you 3 minutes. Okay, so you can pause the video and read it. And the only thing I want you to know, okay, here, note that you have a sonar signal. Sonar signal remember this from the pattern, all this reflected sound waves. Note also that number B is easy as you read it. You will figure out, you will know that you're going to use the wave equation for solving that. The only thing we have to think about is number A. What are you going to do with number A? What's requested here in the number A? So what does how far means here? Okay. So you pose. All right, so how far means distance. Okay, so if you remember from your physics, previous classes in physics, so distance, D, when we divide this distance over the time period that takes the object to cover this distance, this gives you the speed. Okay, so you're giving in this problem the speed of the sound wave, and so this is required. Okay, you are giving also the time, but think about the time. So the time here, the 5 second is the time it took this wave to travel, reflect, and return. So actually the 5 seconds is not the time for the distance covered from the destroyer to the submarine. Actually, the time here is half of this time, okay? Because the sound wave is reflected, okay? So note this common mistake. Okay, so how far the submarine from the destroyer? Again, you could use X or D, whatever you need to use, but note that the time here is half of the 5 seconds. So 2.5 seconds is the time, and you could just plug this here 2.5, and you have the speed, so you can get the distance. Okay. I just plug values and get the distance. It's around 3,825 meters. This is the required distance. The number B is to use the wave equation. To find the frequency of the sonar signal, just use the wave equation. You have the speed. Okay, and you have the wavelengths given to you in the problem as well. So from that you could get the frequency. Okay. And the answer will be around 20 kilohertz. All right, so let's move on and talk a little bit about standing waves. And we start standing waves, usually we start with, or logically we start with resonance. Nearly all objects, when hit or struck or plucked, is somehow disturbed. Okay, and they naturally vibrate. For example, a swing. Other examples that you've studied or encountered in your physics course, simple pendulum, or even if you have a ruler and you hit it on one side, or pressed your finger on one side, it could vibrate. And a very famous example is tuning forks. Okay, so when you hit a tuning fork, it vibrates with a certain frequency. So any object that vibrates will create a sound. The question is, do we hear the sound or not? Sometimes we can hear a sound. The sound could be a musical. Some object just vibrate with creating these frequencies and these sounds that are musical. It could be noisy. It could be loud or low, depending on the wave properties. So for instance, if the amplitude of a vibration are large enough, so this is loudness, okay, the natural frequency is within the human frequency range, then the vibrating object will produce sound waves that are audible, so you can hear them, okay, if they are in the frequency range that your ear can receive. Tuning forks. Tuning fork is a good illustration of natural frequency. So as the tines of the tuning fork vibrates at their own natural frequency, they create sound waves that spread in the air with the same frequency. So each tuning fork has a certain specific frequency. Of course, sound wave that produce with a certain specific frequency. Okay, some object tends to vibrate at a single frequency, and they are often said to produce a pure tone. We call this pure tone, like for example, tuning forks. Okay, this is an example of that. So they produce pure tone, which means just single frequency. But other object vibrates at a set of a frequency, and we call set to produce rich tone. So it's rich tone or pure tone. So these terms just point to either that this object when it vibrates, it creates a single frequency sound wave, or a set of frequencies. Okay, so the frequency at which an object or system vibrates normally when given without outside interference is called natural frequency, or sometimes natural frequencies, because some object or system tend to vibrate at a set of frequencies. Musical instruments are some is another example on that. But let's take this example and in your CK12 text. So you can see in the figure, you can see here in the figure. So here in the figure, you can see this girl is pushing her. So this figure is pushing her friend on a swing. So by pushing in a swing, this will affect the amplitude of the swinging, and we call this forced vibration. When the periodic force from the object or the girl that's pushing affect the vibration of another object, which is the person swinging. In order to get the most swinging effect, the frequency of how often she pushed should be exactly the same as the natural frequency of the swing. What's natural frequency? It's the frequency at which this system, okay, or this swing vibrates normally when giving energy without outside influence. So there is this outside influence or this outside push, but when this outside push just match the natural frequency of the swing, we get the most swinging effect. And you could see here in this figure, there is a small kid that's pushing his dad. So if we do not push at the right timing, okay, but instead push it at some other frequency, the amplitude of the swing will be reduced. So it still swings, but you are not getting the most of it. So we need this resonance. What is resonance? Is the timing of this vibrating force to be the same as the natural frequency. Timing of the pushes to be the same as a natural frequency, and this is called resonance. So if the kid here, okay, he has less force, but if he had the right timing, okay, if the pushes of this kid are timed just right, then even if each single push is very small because he's a kid, okay, less force, even though the force is small, but we have the right timing, the vibration will get larger with each push, okay. So resonance is the timing of the vibration to be the same as in frequency. One classic example of an unfortunate consequence of a forced vibration. So this is a dramatic example, but it's usually cited. So it's good to know about this. And also your associated assignment with this video is related to this example. So this example is what happened to the Tacoma Narrow Bridge in 1940. That's a dramatic thing. So what happened here is that this Tacoma Narrow Bridge was built in Washington the 30s and opened only for 4 months. It was the third longest suspension bridge in the world at this time. It was covering about 6,000 feet. So what happened is that it collapsed because of the wind. The wind was very fast. You have very strong wind of 40 to 45 miles per hour. And this bridge was very narrow and was a suspended bridge, very long and very narrow. So when it collapsed, it was revealed that the engineers had not probably considered the aerodynamics forces that were in play at the location during the periods of strong wind. And it was not actually like, I mean, it was their fault, but these kind of aerodynamic forces were not taking into account during these early times. So it's commonly were not considered because they thought, okay, the forces coming from the wind is not very high anyway. It's small. It has usually it has small effects, and they have also these strong steel columns. So they thought, okay, we'll not take this. Usually we do not take this into account, but for this case, because the bridge was very narrow and very long as well, it has a great effect. So in November 7th, 1940, high winds baffled the area, and the wind speed was very high, 42 miles per hour or higher, and the bridge swayed considerably. The wind caused the bridge to toss back and forth wildly, and so this thin narrow bridge resonated with the wind, okay, with the force coming affecting it from the wind. And when the bridge experienced very strong winds from a certain direction, the frequency of oscillation built up, and to such a degree that the bridge collapsed. And this is a very sad or dramatic example. But I mean, from this time, engineers begin to research and to take aerodynamic forces into account, especially for suspended long bridges like this one. Okay. So your assignment for this your assignment for associated with this lecture or this class, you're gonna okay, you can pause the video, you check the link here, it's on history.com. Okay, you'll and it's about the Tacoma Narrow Bridge. So you could, it's a short article, will not take you more than 10 minutes or maybe less. So you read the article, and then in a separate sheet of paper, explain the following sentence. So this is a sentence that you should explain. Although the towers of the Tacoma Narrow Bridge were made of strong structure of carbon steel, it collapsed. So why is that? Okay. I mean, the answer is not hard for you. So just write the answer in a separate sheet of paper, email it to me, or share it with me like before. And so that's your assignment here. That's your associated assignment. All right, so let's move on to your lab, microwave. So we come to the microwave lab. So I try to place this in a very very clear way. It's unlike the video. So first thing to do here, first step, to watch the video. Okay, so first thing to do, just watch the video, microwave lab, that's posted on Google Classroom. It's a 5-minute 6-minute video. Just watch it. I know the video is not the greatest thing. I could make better, but I mean it needed some editing. So just watch the video, follow the steps, and perform this lab. Okay, and you will know from the video, you can know that what materials needed, microwave, chocolate bar, a ruler, and this kind of things. The thing that's missing from the video or not clear in the video is the time that you heat the chocolate bar in the microwave oven. As the time here is 15 to 18 seconds. Okay, so this is not this time period is missing from the video, so I'm emphasizing that. So just leave it or heat the chocolate bar in the oven for 15 to 18 seconds. Another thing I mentioned in the video, but I don't know if it's clear. I don't think it's very clear. I have to emphasize it again. So if you could locate only so if you could locate 2 notable melting spots on the surface of the chocolate bar, Even if you flip the chocolate bar, if you have to flip the chocolate bar, that's fine. But if you locate only one notable melting point, like one big melting spot, look for a smaller melted spot closer to the notable point that you could locate. You might need to press by your finger on the surface of the bar. So usually this represents a throw. So if you measure the distance between those 2 points, the one that's notable and the one that's not really, the distance need to be multiplied by 2. So usually this distance will be maybe 6 centimeters, 5 centimeters. So this is just a half wave length. So you need to, in order to calculate the whole wavelength of the microwave, you need to multiply this by 2. But if you can spot two points that are notable melting spots, and you could measure the distance between them, that's fine. So after you do that, complete the lab sheet, post it on Google Classroom, and it's very simple. You don't have to write the steps. Just do some calculations. And in the conclusion, just write like 2 sentences about the lab. If your reading is much higher than the speed of light, you have to mention that. You have to comment on that. If the result is much lower, like something very low. So lower and higher, I mean here like 2 digits or more. Okay. You have to comment on that and to comment on that in your it's not a lab report, it's a lab sheet. Okay, so have a great rest of the day. Do not forget to submit your lab sheet before Thursday 10 p.m. Okay, so have a great rest of the day.